So, greetings from a hotel room in the middle of Iowa because Mr. Nendick didn't actually make this video before leaving. Anyway, today we need to work on titration and neutralization. And those are two topics in chemistry that actually are pretty important. Titration and neutralization are things we do with acids and bases all the time. A titration lets you say, okay, I have this chemical, what's its pH? Without using a pH meter, how much is dissolved in it? Can I do some math to understand a little bit about the chemistry behind it? Neutralization on the math side of things says, how can I take this acid and turn it into a base? Or I add this much, what's the pH going to change? Sometimes your chemical reaction only happens, let's say, in an environment where your pH is greater than 13.5 or only in a strongly acidic environment. And you say, okay, well, how much acid do I need to add so I'm not adding in excess? Because sometimes if you add like excess sulfuric acid, let's say to potassium permanganate, you get an explosive called manganese heptoxide. It's a big common problem in organic chemistry. Or if you add too much base, sometimes you'll destroy the molecule you're trying to make. So we need to know, okay, sometimes we need to get here. Sometimes you have a problem where you have to say, okay, I have an acid, how much of this do I have to add to make it no longer dangerous? Actually, it's something we encountered today in robotics. We had a battery break and the sulfuric acid in the battery started coming out, and we had to figure out how to quickly stop that from eating our robot apart. It may have been a longer day in the robotics world. Anyway, as this goes along, I'm going to do two things. I've got some videos from the lab I took before I left, and I want to show you the lab techniques we're going to be using Monday and Tuesday. And they're a little disjointed, but in the same breath, if I were doing this in a classroom, it would be a little disjointed. Until you get your hands on the tool, it's going to be hard to know exactly what to do. And the second thing we need to do is go through the math. You're going to have two of these problems for homework over the weekend. I don't think they're going to be too terrible, but I understand they're a level of difficulty above the pH square. And so I want you to at least get an attempt at that as we come into next week, because we're looking at test again, probably next Thursday or Friday is the goal. So without further ado, let's head to the lab and let's introduce some new glassware, starting off with something we call the Burette. A Burette is a long graduate cylinder. You can see it's got numbers running the whole length of it here that terminates in what's called a stopcock, which is just a valve that comes to a narrower piece of glass. This valve here is closed when it's kind of orthogonal to the tube, and if you turn it parallel to the tube, that's open. So liquid flows out there. This stops liquid from flowing out. You'll note the numbers here end at like 50 and start at the top at 0. Well, that makes sense because we don't know this volume here from the line down, or the volume inside the valve body here, or in its nozzle. But we do know where we start, and as the water drains, we'll know where we end. And of course, that leads us to a pretty interesting little thing in math, which is called delta. Delta, remember, means the change in something. So we have a delta here. In this case, we have a delta volume, delta V. And delta V is just going to be as simple as the volume that you ended at minus the volume that you initially are at, which we call V naught in math. That number will, of course, always be negative in this case. So for us, we can actually just say, in this particular case, we can kind of redefine it and understand that we're going down and kind of do away with the sign. And we're going to get the same magnitude of the number, just opposite sign. It doesn't really matter which way you do it. But you're going to see how much you started with and how much you ended with. Please note that this is a very narrow tube. So we're actually accurate to 1/10 of a milliliter, right? There's 10 graduations between here, like 38 and 37. And actually, you can estimate another significant figure from that. So this is actually quite a precise piece of glassware. And as a result, they are pretty costly pieces of glass. They're probably the single most expensive piece you'll use this year in chemistry. So do handle them with some caution. To set up a burette, you just take it here, and you're going to use if I can use my viewfinder here, it's surprisingly hard to do with two hands. Where the heck is it? Mr. Neck is just going to edit this piece out later, I think. Aha, there it is. Use a clamp, a 3-fingered clamp, and you'll slide it in and have your partner tighten both set screws. Now it's important that you don't over-tighten those screws. You can squeeze it too tight and shatter the burette, and you'll be out 40 or 50 bucks and out lab results, so don't do that. And in the same breath, you want to make sure it's tight enough that it doesn't just fall straight on the table and break the tip. No, of course we can replace the tip There'll be the expensive parts, the graduated part, but still, be careful when you're setting this up. All right, now everything here is set up for a rough titration. Now you can do these things with a little more complexity. Eventually you may in lab with like a magnetic stir, an electronic pH meter, and stuff like that. But for right now, you have a reaction vessel, which is just a 100 milliliter beaker with some reagent in there, probably just a acid. And you have the tip of the burette up to the stopcock, and then the body of the burette being held up by a 3-finger clamp, and up to the top where there's a mini funnel to help fill. Now the first thing you're going to do is you're going to need to read the burette. This can be difficult to do. So you hold up a piece of paper, find the meniscus, there it is, and you actually count from the top down. So this is 5, and level with it, there's the half-like. So this is 5.5 milliliters. And without going through exactly what's going to happen yet, we need to do a little bit more work with the lesson first. You would flow some water or some base or whatever your titrant is up here into the titration. Turn it on. And what you don't want to do is just have like a jet of water like this come out. That's not useful. You want this to be just open just enough. Close it back. Closing. To just drop-wise. And something will happen eventually. That's something we'll have to talk about and then come back and see. But now we're adding a very, very steady stream of whatever's in our burette to the reaction vessel. So we try to refocus this here. It's surprisingly difficult to do this with one hand. And you can see, even though it's dripping, that water level is falling like 1/10 of a milliliter per drop, give or take. About 10 milliliters, or 1/10 of a milliliter per drop. Right, just a little bit at a time. Well, as it's doing that, as this is falling in, you're slowly trying to create a mixture of acids and bases to neutralize the two, to basically make a pH of 7 and an ionic salt. And that's it, that's a titration. Now we'll have to use an indicator or a pH meter to know that, but this apparatus here, this is how we're going to do that. You know, this is flowing, and it's very easy to control this because there's such a... And eventually, whatever we need to happen down here will happen. And at that point, you'll quickly flip the titration over. And then you'll come back up, and you'll find the meniscus and read the value. And you can see the value here ended off. Let's see, there's 22, here's 23. Probably like 23.1, 23 point, well, here's the bottom line. 5, 4, 3, 2. So I'd argue that's 23.2. Okay, so you can see here is where we ended off. Now I just got a piece of paper back here to show the meniscus. Here's the 22, here's the 23, here's the 24. So there's 23.5, 0.4, 0.3, 0.2, 23.2. So our final volume in this case is 23.2 milliliters. And whatever we started with, we can do the subtraction. And we know that's exactly how much liquid we added to the titration. Neat. So we need to introduce another character. It's someone we've worked with before, but probably a little more important now to us, and that's called phenolphthalein, that big word there. And it's a white powder. Here for a second, let me open that up. And you can see phenolphthalein is just a white powder. It's a very kind of dusty, almost looks like baking soda consistency powder. It's actually pretty easy to make. There's a smell that's got this kind of sweet, almost sarsaparilla smell to it. It's very pleasant. Phenolphthalein has kind of a storied history in chemistry. It actually started off as a laxative among its uses, and it fell out of use in that way, like many sweet-smelling things like it. Once it was discovered, it was a very strong carcinogen, so it took care of your immediate needs and then gave you cancer down the line. So phenolphthalein, as long as you don't eat it, is perfectly safe, so just don't stick it in your mouth. How we use it in a lab is we dissolve it in ethanol. It's not soluble in water. It's very weakly soluble in water, more correctly. And so we need to dissolve it in something, and alcohols tend to dissolve it. So it's just a simple solution to make, and you'll often work with phenolphthalein. Now, phenolphthalein has one really unique property. So in certain solutions here, it turns them deeply purple. Kind of cool, very pretty color change. This has to be a base. When something stains phenolphthalein, like this, that's a base. Contrarily, in an acid, it does nothing. You can see it's white there. That's the phenolphthalein, the solid. in the water, but nothing. So over here we have an acid and a base, as indicated by phenolphthalein. You can see that phenolphthalein needs a pretty good mixing to actually stain the whole solution, but it easily will. It doesn't take a lot. So if we put phenolphthalein in an acid and we add base to it, at the point when the pH crosses from like a 6 or a 5 when it's an acid, through 7 when it's water, it reaches up there to like an 8 when it becomes a very weak base, well, the water's going to go, or the solution's going to go from clear to purple. So we'll know that we've hit what we call the equivalence point. It's a real neat chemical that way, and it works very, very well. It's a little easier to use than, let's say, the cabbage cloth thing we made. One more interesting thing is if you take a base here stained with phenolphthalein and you pour it into an acid, which is the opposite of how most titrations would work, you actually see that purple color being eaten up by the acid. And it lingers a little longer the more I add, like there, you see it lingering. And that means we're getting close to the equivalence point. Add just a little bit more, lingers a little longer, and just a little bit more, and it will actually stain the acid purple, signifying we've gone from an acid to a base. Just like that. So this indicator can tell us a little bit what's going on in our reaction vessel here without having any instruments in there. And that's going to be how we judge a rough titration. So let's say you're working with some acid here. This is just 1 molar HCl. And, you know, you've got some 1 molar HCl here. Let's try to measure that volume really fast. Oh, I'm klutzy. Oh, God, I'm adding water. Oh, that's a mistake. Oh, I have no idea what that is. So now I've got a problem in a lab. You know, I can't just stick a pH probe in there and say, you know, what's the pH, and work backwards and figure out the concentration of the acid, because pH probes aren't that accurate. I need a really precise way to know what I just did. Like, I just diluted that. I don't know how much acid I had in there, and I added water to it. You know, and now I need to know what the concentration of this acid is. What's the hydrogen ion concentration? But it's actually quite a common problem in chemistry. Let's say you make a solution, you want to figure out the pH at the end of it. This is the most accurate way of doing it. It's called titration. And so what we're going to do here is introduce you to how you do a titration properly. So let's take, I don't know, 15 milliliters. That's going to be our initial volume, 15 milliliters of this acid here. So really quickly, I'm going to pour it. And there it goes. And being accurate here actually matters quite a bit. And so like this would not work for me. That's 16 milliliters. That would definitely invalidate my results. So I'm going to use an eyedropper and adjust it and bring it down to 15. Alright, so now that I've made that exactly 15 milliliters, I'm just going to add that 15 milliliters of acid into my reaction vessel, making sure to get everything into there. And I'm going to fill up my burette with some base. Now I've carefully prepared exactly 0.100 molar sodium hydroxide. And I just need to add that to my burette. Now it's important to do something when I add it to a burette. I need to make sure the stopcock is closed. If it's not exactly closed, I'm just going to be pouring base into here and not be quantitative. So I'm going to use the funnel here, and I'm going to pour it in while lifting the funnel out of the burette a little bit so air can escape as the liquid comes in. So I'll do that now. I'll need both hands. I need to stop filming this for a second. Okay, so now we can see exactly, hold on. Okay, so now we can see that I filled this up, and we need to read. So we read from the top down. So 2.6, it looks like, 2.6 milliliters. So I'm starting off with V naught of 2.6 milliliters. Now what I'm going to do is I'm going to take some phenolphthalein, down here, and with a little bit of focusing, I'm going to just add a couple drops to my reaction vessel. And you can see it doesn't do anything, of course, because we know that's an acid. And now I set up a basic stirring apparatus. And now we'll know that the pH is 7 when the phenolphthalein flashes to purple. So the first thing I do is I'm going to turn on and adjust the stir rod here until it's just nicely, gently stirring. And I'm going to turn the stopcock until I get a nice, gentle drip. Something like that, right about there. See it coming, and There we go. Adding dropwise is what a chemist would say. And because this is a long process, I just kind of have to sit here and wait and wait for this to turn purple. It's going to take a while. So for that, I'm going to speed it up.
A few moments later.
You can see as the base hits the acid, it flashes purple for just a moment as it reacts with the phenolphthalein. And then it gets mixed through and back throughout the whole solution, and that base is reacting and neutralizing, and the solution remains acidic, so the purple goes away. You'll notice you get closer to the equivalence point, that purple will last longer and longer.
A few moments later.
Alright, so what I want you